Let's talk about pressure. Pressure is defined as the force exerted over an area. So it's not just force, but in a sense, how concentrated the force is. For example, the cone up here has a certain amount of weight, and it would exert a force on a table if it was sitting on top of a table. The amount of pressure it exerts would be that weight divided by the area of its base. Now, if we took that cone and we flipped it upside down, it has the same exact amount of weight, but a very, very small amount of area that it's exerting its force over. The pressure would be significantly greater if the cone was flipped upside down. So it's not just about force, but it also includes area. The units of pressure would be, of course, the units of force, newtons, divided by the units of area, which would be meters squared. Now, we do have a shortcut for that, and it's named after Blaise Pascal, famous mathematician and scientist, and it's called the Pascal. So Pascal is exactly equal to 1 Newton per meter squared. In chemistry, you probably use the units of atmospheres or millimeters mercury or torr, and those units make plenty of sense for certain applications, but in physics we like to use pascals because it's consistent with our units of newtons and meters. What I'd like to do right now is derive a formula for the pressure exerted by a liquid at depth. And we're going to talk about liquids and not all fluids because gas pressure is a little different, a little bit more complicated, not something we cover in our course. But imagine the cylinder over here is filled with fluid. Let's say it's a glass. The pressure exerted on the bottom of the glass would be, of course, the force exerted by the weight of that liquid divided by the area of the bottom. So we'll say that there's a certain area down here. And we're also going to say that the glass is filled to a certain height with our fluid. So the force that we're talking about is the weight of the fluid divided by the area of the bottom. When we talked about density, we learned that density was defined as mass per volume. And we also saw that you could solve that for mass, and you would get mass is density times volume. Since we're talking about a volume of fluid here, we're going to substitute this mass expression, density times volume, over here into our expression. And what we're going to get is that pressure is now equal to density of the fluid times the volume of the container, or the volume of the fluid, times G over the area. Now, the volume of this fluid is equal to the volume of the cylinder. And the volume of a cylinder can be expressed as the area of the base times the height of the cylinder. And of course, we're subbing that in for our volume. And what you might notice here is that our areas are going to cancel out. So with the areas gone, we have something. I'm going to do a little rearranging here. Pressure equals density times G times the depth. Okay, so the area of the bottom doesn't matter. It's just the height. And this expression, and this works really well for fluids and not for gases because fluids are incompressible and the density doesn't vary with depth. Okay, so let me rewrite this expression. Pressure equals density times G times H. This form of pressure is actually a pressure difference. It's the difference in pressure from the top to the bottom. Sometimes this is called the gauge pressure. And this is not actually the whole story. So if our fluid happens to be open at the top, it's also going to have some weight of air bearing down on it from above. The atmospheric pressure pushing down on the top adds to the total pressure. Atmospheric pressure, which we will represent as P0, is, we're going to round this off in our class to 1.0 times 10 to the 5 pascals. It varies, but that's a good one to use in general. The actual pressure at the very, very bottom of our container is called the absolute pressure, and it's equal to that atmospheric pressure plus our gauge pressure. or rho GH. This, again, is called our total or absolute pressure. Sometimes you don't need to include the atmospheric pressure. If you have a container that is not open to air pressure at the top, then you don't need to add it in. But this is kind of the general equation we're going to be using for fluid pressure. All right, let's do a little example. What depth does a diver have to dive to reach a pressure that's twice normal atmospheric pressure? So first of all, normal atmospheric pressure is about 1 times 10 to the 5 pascals. So the pressure we're trying to reach is double that. So we're aiming for a pressure of 2 times 10 to the 5 pascals. What we can do here is we can take our formula. Let me write it down first. The absolute pressure is the atmospheric pressure times the density of the fluid times G times H. Now, in this case, what we want to do is we're actually solving for H. Now, H, it says depth, but this is a height, so to speak. It's a vertical distance. So what we want to do is solve this thing for H, and we'll have our answers. So let's take this and do a little algebra here. So I'm going to subtract atmospheric pressure from both sides. And then I'm going to divide both sides by density and G. And so I will get that my height is the pressure we seek minus the atmospheric pressure over density times G. At this point, all we really have to do is plug the numbers in. So we'll take our pressure, 2 times 10 to the 5 pascals, minus atmospheric pressure, 1 times 10 to the 5 pascals. And this whole thing is going to be over the density of water, which is 1,000 kilograms per meter cubed, times 9.8 meters per second squared. If you do that out on your calculator, we come out with a value of about 10.2 meters. It's about 30 feet. So if you were to dive down in water at 10.2 meters, you'd be at a pressure that is twice normal atmospheric pressure.